MOSFET like a really smart, voltage-controlled water faucet. In this diagram, the base is a P-type silicon substrate. Inside it, you've got two separate N-type regions. These are your source, like the water inlet, and your drain, like the outlet. Now sitting above the gap between them is the gate. This is your control handle, and it's electrically isolated by a very thin layer of silicon dioxide, so no direct current flows into it. Now, let's look at what's happening here. This MOSFET is in its default state, off. The voltmeter shows the gate-to-source voltage, VGS, is 0 volts. So, we're not applying anything to the gate. That means the handle isn't being turned. Because of that, the gate has no influence over the channel. The P-type material between the source and drain stays as a solid barrier. And the result? The path is completely blocked, like a closed valve, and no current ID can flow from drain to source.
Thanks, Gigi. Now let's go over how to turn it on. To turn the MOSFET on, we apply a small positive voltage to the gate. In this diagram, you can see it on the voltmeter as VGS equals VTH, the threshold voltage. So what's happening here? That positive charge on the gate starts acting like a magnet. It pulls in mobile electrons, those little red dots, toward the surface, just beneath the insulating layer. Now we're starting to see a change. Those electrons begin forming what's called an inversion layer, basically a thin, fragile, conductive path that starts to connect the source and the drain. At the same time, that wide depletion region from before, well, it gets pulled in and becomes much thinner. So what's the result? The channel is just starting to form. It's like the valve is barely cracked open, and only a small amount of current can begin to flow.